Hello all, thank you for inviting me to speak in this geometric analysis past, present and future spring 2022 session. Uh, I will be speaking on this project which is a part of my PhD done in collaboration with Filippo Mazzoli and Andrea Seppi, which talks about CMC foliations of quasi-Fuchsian manifolds near the Fuchsian locus and Hamiltonian paths in the cotangent space of the Teichmuller space. So without further delay, I'll just start with what we are speaking about today. So we take S to be a closed oriented surface of genus G greater than equal to 2, and gamma is the fundamental group of the surfaces. So we want to study the action of gamma on H3 and subsequently study the space which is H3 mod gamma, where gamma is a discrete subgroup of PSL2C. So what is happening here is that we always have a holonomy representation from the pi 1 of the surface into PSL2C, and this image that you have is what we call as gamma, and being a discrete subgroup of PSL2C, it acts properly discontinuously on H3, as PSL2C is the group of isometries of H3 which preserve orientation, and as a result this gamma action on H3 is well defined and in fact free and properly discontinuous, and we can consider the manifold H3 mod gamma. However, if you take the boundary at infinity of H3, which is identified with the complex projective space CP1, which is essentially the sphere, then the action of gamma is properly discontinuous and free in the complement of the limit set, where the limit set is the set of accumulation points of orbits of gamma under the action. So it means that basically I'm taking this limit n going to infinity gamma n on x, where this is the action and gamma is an element of this gamma and x is a point in H3. So given this scenario, what we are going to do is that this H3 mod gamma in either of these cases will look like a surface times the real line, and what we are going to do is classify this manifold M, as we would call, on the basis of the shape of this limit set. So we will call M as Fuchsian if this lambda gamma is a circle on the boundary of H3. So that means that the limit set is actually an honest circle, and in this case what you can say more is that this gamma is conjugate to a subgroup of PSL2R, which is fixing H2 inside H3, as PSL2R is indeed identified with the group of orientation preserving isometries of H2. So if this is the Fuchsian case, then what is the quasi-Fuchsian case is that in this case this limit set is not a circle but a quasi-circle. One more way to be precise is that there is a quasi-conformal map from the CP1 to CP1 and a Fuchsian group gamma 0, such that this gamma, which is the quasi-Fuchsian, is conjugated to the Fuchsian group by this quasi-conformal map. In essence, I am having a quasi-conformal map which is sending this circle to a quasi-circle, and in both the cases the quotient that you get is looking like this surface times the real line. Well, you could say that in the Fuchsian case you will have that this induced conformal classes at the boundary would be the same, wherein in the quasi-Fuchsian case they would be like different. So this is actually something called the Bayes simultaneous uniformization theorem, where it says that the quasi-Fuchsian manifold can be uniquely parameterized by the complex structures appearing at just the two end in their like up to equivalence, and yeah, so one of the demarcations between Fuchsian and quasi-Fuchsian is that the complex structures appearing at the end are same and not the same respectively. So what we will do is that we will denote the space of quasi-Fuchsian matrix as on S cross R as QFS, and Fs to be the Fuchsian matrix, both up to equal up to diffeomorphisms isotopic to the identity. And moreover, notice that this Fuchsian locus is identified with the classical Teichmuller space, which is the space of hyperbolic matrix on the surface up to diffeomorphisms isotopic to the identity. Well, every conformal class or a equivalence class of complex structures contains a unique hyperbolic metric, and this is essentially the identification. And moreover, you can see that the space Fs is included in the space QFS uh, quite naturally. So what you want to do now is that given is quasi-Fuchsian manifold, actually there is something that should be mentioned here, is that once you have the limit set, what you can do is construct the convex hull of it, which gets quotiented to something called the convex core of the quasi-Fuchsian manifold. Well, the Fuchsian manifold also has a convex core, but in that case what you have is that it is essentially the geodesic copy of the surface inside the manifold, seen as a quotient of the copy of H2 that was there in the copy of H2 which had the boundary as the limit set in the Fuchsian case. So if this is the Fuchsian picture, then this is the quasi-Fuchsian picture, and the convex core is the smallest non-empty convex set that is contained in the quasi-Fuchsian manifold, and it has two boundary surfaces which are kind of the hyperbolic surface but bent along certain uh, geodesic lamination. You don't need that for this talk, but what we are trying to do is we are trying to foliate this region which comes between this splitted surface and the boundary at infinity. So we are trying to find a foliation of this region which are called hyperbolic ends by constant mean curvature surfaces, where the value of h will range from -1 to 1. What do you mean by constant mean curvature surface is that, as I have written, if you have a surface inside a bigger manifold, or in particular this quasi-Fuchsian manifold, then it would come with the first and the second fundamental forms. The first fundamental form is telling you what is the induced metric, and the second fundamental form is telling you the variation of the normal of the surface as you move along the surface of the normal 2s. So given these two datas, these are two tensors essentially, and what you could do is define something called the shape operator, which is this essentially this I inverse of 2, and you want this trace of the shape operator I inverse of 2 to be constant on the surface. So given this situation, what we prove is that if you had remembered that the Fuchsian locus is included in the quasi-Fuchsian space, so if you have this Fuchsian locus inside the bigger quasi-Fuchsian space, then there is a neighborhood of the Fuchsian locus which has this property that every quasi-Fuchsian manifold U in this neighborhood contains a smooth, unique monotone CMC foliation with the values of the mean curvature ranging in -1 to 1. So why and there is a second part of the talk as well. So what do we do in the second part of the talk? So this proving this would be the first part, is that if you are given the CMCH surfaces inside this quasi-Fuchsian manifold, what you could do is that you could define a point in the cotangent space to a Teichmuller space. The points in the cotangent space to a Teichmuller space typically look like a conformal class and a quadratic differential defined on the conformal class. Or a complex structure which is equivalent for a surface. Quadratic differentials are objects that locally look like the form fzdg square, and what they do is that they define cotangent vectors to the Teichmuller space at the given point C. So if you are given the data of a CMC surface, this traceless part of the second fundamental form so happens gets identified to a real part of a quadratic differential, and this is the quadratic differential that you get out of a CMCH surface. And of course, the induced metric up to equivalence gives you a point on the Teichmuller space. So given these two points, this data of a CMCH surface, what we want to do is that for a fixed manifold, we want to consider this path H, which goes from H to the corresponding values of the first and the second fundamental forms essentially. And what we want to show further is that this path is the orbit of a time-dependent Hamiltonian flow defined in an open neighborhood of the zero section of the cotangent space times -1 and 1. The -1 and 1 product to the cotangent space just keeps a record of the time parameter, which is the capital H here. And what we can further show is that the Hamiltonian function is the area of the CMC H surface in M, but up to a multiplicative constant equal to -12. So these are the two works that we are going to present. This is actually not out yet, but it will be soon, as in archive, and the previous work is already there. So what we are going to do is now kind of motivate why we want to study these things. So quasi-Fuchsian manifolds are an important class of three manifolds that have been studied by Thurston and many other experts. And there are these are centers that these quasi-Fuchsian manifolds are is a like center for some problems and conjectures. One of them being this CMC foliations near the Fuchsian locus in some sense. I will be precise more. So if you just focus on this works of like CMC surfaces in quasi-Fuchsian manifolds under various assumptions, I mean, where do they appear and what is the constraint on H we have, then there have been some works. So one of them is what is of quite importance to us are the works of Marcel Packard and Quinn that show that the ends of quasi-Fuchsian manifolds are foliated by a CMC surface with mean curvature in -1 to -1 plus epsilon and 1 minus epsilon to 1. So what do I mean by an ends of quasi-Fuchsian manifold? That I have the boundary at infinity. So the boundary at infinity would be uh, copies of two disjoint copies, union of two disjoint copy of the surfaces. And I take an epsilon neighborhood around the boundary at infinity. And then what these two results show is that there is this neighborhood which contains a foliation by CMCH surface for any quasi-Fuchsian manifold. But the data of the CMCH is will be in -1 to -1 plus epsilon and 1 minus epsilon to 1. You can imagine kind of that the quasi-Fuchsian manifolds, the boundary at the ends kind of act. I mean, you don't really have an honest CMC-H surface in a quasi-Fuchsian manifold with the CMC-H equal to 1 and -1, but uh, what you could kind of imagine that wherever you are in the quasi-Fuchsian space, you could perturb this data at infinity to get some CMC foliations or CMC-H surfaces near the ends, which have these values of mean curvature. We are going to actually go through the proof of it, and you will be more clear about what I'm going to do about this perturbing the data at infinity part. Apart from that, there are these results of Koskunzer and Guaracolima Paet in 2016 to 18 and 2021 respectively. Well, Koskunzer has results on existence of CMC surfaces in H3 or quasi-Fuchsian manifolds under various assumptions of the values of H. And more recently, Guaracolima Paet have shown that there exists a foliation of a quasi-Fuchsian manifold that is by surfaces which have the constant sign of the mean curvature. Well, not really constant mean curvature, but it's in a similar spirit. What more you have is that you know that in general a quasi-Fuchsian manifold does not admit a global CMC foliation. I would like to say that this example of this quasi-Fuchsian manifold not admitting a global CMC foliation is pretty closely related to these examples of quasi-Fuchsian manifolds not admitting a unique minimal surface. And you could kind of consider that in this foliation by CMC surfaces in H1 -1 to 1 that we construct, this H equal to 0 is actually this minimal surface. And In fact, if you just restrict to quasi-Fuchsian manifolds containing unique minimal surfaces in with values of principal curvature in -1 to 1, then you reach this almost Fuchsian space. So what is this almost Fuchsian? I would like it as AFS, as these quasi-Fuchsian with a unique minimal surface with uh, principal curvatures in -1 to 1. So this has been also centered of work of Uhlenbeck and others. And what happens is that this almost Fuchsian manifolds, this set of almost Fuchsian manifold again form an open neighborhood of the Fuchsian locus. If you go back to this picture that I had drawn, and what open set U we construct is going to be contained in the almost Fuchsian locus. So, in fact, there is a conjecture of Thurston that although quasi-Fuchsian manifolds cannot be foliated by CMC surfaces, almost Fuchsian manifolds can be. And this is what we partially answer in some sense. So yeah, I mean, yeah. So so yeah, about the motivations, about the second part of the talk, what we have is that this foliation of CMC hypersurfaces are useful in the study of Lorentzian manifolds as well. So in Lorentzian setting, you can show that you have a foliation by CMC surfaces, and there are some implications of it to physics that I would actually sound a bit pretentious about, and I don't really have a good understanding. But what happens is that if you write down so what there is a work of Moncrief in 1989 which shows that this data of the CMC8 surfaces in Lorentzian setting kind of associate to a reduction of these Einstein's equations to some Hamiltonian flow on the cotangent space of the Teichmuller space, and this is kind of what influenced uh, our work as well. I mean, although we don't have a clear physical interpretation of what we were going to like see, but this being done in the Lorentzian setting kind of motivates the hyperbolic question. And actually, there are other kind of foliations that appear between this boundary of the pleated surface and boundary of infinity, which are by K surfaces. So these surfaces, instead of the constant mean curvature, have the fact that they have the constant Gaussian curvature. Uh, uh, and K-surface foliations have been shown to exist for any quasi-Fuchsian manifold, I think initially by Labouri, and what we want to do is kind of emulate the property shown by Mazzoli in 2021 that these K-surface flows actually form time dependent orbits of time dependent Hamiltonian flow, where here also the Hamiltonian function is the area of the K-surface that you have. So we will continue with now the existence of CMC foliations near the Fuchsian locus, which is the part one of the talk. So what we are going to do is that we are going to break the proof down into two steps. We are going to first show existence of a CMC surface with H in minus 1, 1 in a quasi-Fuchsian manifold near the Fuchsian locus. And for this reason, what we want to do, so first we will show that the CMC surface for any values of H exists. Then we would construct a foliation out of it. And what we will like to do is that we will first show the existence in a compact part. So a compact part would mean in the complement of the ends, because you know that the ends are already foliated by CMC surfaces. And to do this, what would and this compact part near the Fuchsian locus is where we actually are working in the neighborhood of the Fuchsian locus. To do this, what we will do is that we will use two parametrization of quasi-Fuchsian we will use a parametrization of quasi-Fuchsian manifolds by these Schwarzian derivatives, and the other part would be to use that data at infinity to construct this Epstein surface inside. And essentially we will try to find solutions to when this Epstein surface can be a CMCH surface, and this happens near the Fuchsian locus is what we show. And then when you have these CMC surfaces in quasi-Fuchsian manifolds, what you would like to do is that you would like to construct this diffeomorphism from the surface times minus 1 to 1 into the manifold, such that the image of every h is the CMC surface in M for all values of h in minus 1 to 1. And this requires a bit of more work using this geometry maximum principle, essentially to claim that this map is injective. And then upon showing that this diffeomorphism exists, what we prove essentially is this manifold M is foliated by CMC surfaces. So I'll go to this Schwarzian derivative at infinity parametrization of quasi-Fuchsian manifolds now. So if you had been in this universal cover picture, then you had this limit set, and the complement of this limit set are these domes that you could always uniformize and to the disk. And if you consider this uniformization map phi, it is holomorphic. And in such a situation, what you could do is that you can consider the Schwarzian derivative of this map, which gives you a quadratic differential here. The Schwarzian is defined in this way, as I have written, phi double prime by phi prime minus, so there should be a prime here, actually the derivative, minus half of phi double prime by phi prime whole square dg square. And property of the Schwarzian derivative is that the Schwarzian is zero if and only if this phi is a Mobius map. So as you can see in the Fuchsian locus, the Schwarzians uh, vanish, because I mean, in that case I actually have an honest circle and I'm sending this disk to a disk, and it's just like some Mobius transformation that is doing that. And the Fuchsian locus does get parameterized by this data at infinity with no quadratic differential, basically just the conformal class of the metric that is appearing. And this also gives us a homeomorphism between the space of quasi-Fuchsian manifolds and the space of quadratic differentials, which is a homeomorphism onto its image, basically allowing us to identify a quasi-Fuchsian manifold with the data at infinity. Now, given, so suppose this was my quasi-Fuchsian manifold and this was my data at infinity, or here in the universal covered picture, this was my quasi-Fuchsian limit set correspondingly, and this was my data at infinity. What you could do now is that you could construct a surface inside H3 that somehow captures this data. So what is this? Is this Epstein surface? So given, so for defining the Epstein surface, we would like to define something first, which is the visual metric for a point at the boundary but seen from a point inside H3. So what is this? That given a point P inside H3, you have a point Z on the boundary, and you could take the unique geodesic joining P to Z and push forward the unit ball at P to the unit ball touching the point Z or tangent to the boundary at Z, and this induces a metric at Z, right? And that is what we call the visual metric from the point inside, seen from the point inside at the point Z at the boundary at infinity. Now, what this Epstein surface do is that if you are given a conformal metric or some conformal metric uh, at a domain on CP1, it gives you a surface inside such that the visual metric seen from the surface is equal to the conformal metric given. So to be precise, that given a CK conformal metric G on a domain omega in CP1, there exists a unique CK minus 1 map Epstein G from omega to H3 such that for all values of Z in omega, we have the visual metric seen from the Epstein surface is equal to the given metric. Uh, if you really want to go into a bit further details, but not really, then you could imagine that there is this one-to-one correspondence between conformal metrics at the boundary of infinity at H3 and horoballs based at H3 at the boundary of infinity at H3. This could be shown as you could take this unique geodesic line and then the geodesic plane orthogonal to this geodesic line, and then there would be a unique horoball trapped in between this geodesic plane which is tangent to Z, and the visual metric seen from this point would be kind of a one-on-one correspondence between with the horoball that you can uniquely fix in this region. And now, given a conformal metric, what you could do is that reutilize this correspondence to get this collection of horoballs at every, sorry, this horoball at every point. And this surface that you get is essentially the envelope of all these horoballs, like a surface which is tangent to all these horoballs. You well this push forward of the unit ball to this boundary is what is called the asymptotic Gauss map. And one another way to kind of motivate this Epstein surface is that suppose you had this Epstein surface has an induced metric I, then if you pushed it forward by by this Gauss map, then it would give you back the conformal metric, but up to some scaling, say. So this is what you are getting in an Epstein surface, is that a surface which is giving you back the metric. So given a metric at a domain, this is a surface inside which is giving you the metric upon identification with the Gauss map and up to certain scaling. So so this gives a kind of correspondence between data at infinity and surfaces in H3. And in general, this Epstein surface may not be an immersed surface, as you can take the omega to be the whole of CP1 with the spherical metric, and then the Epstein surface would just be a point. And of course, this image is what we call the Epstein surface. But what is of importance is that given this data at infinity, we could formulate a formula for the first and the second fundamental forms of this Epstein surface as an expression of the C tilde Q tilde or the conformal class at the Schwarzian at infinity. And what we would like to do is that we would like to claim that this Epstein surface is a CMCH surface. So there will be, suppose you have C and Q, then this mean curvature of the Epstein surface of C would be given as a function of C Q H. And actually what you do is that you take the C to be some e power 2u times the hyperbolic metric in the conformal class, and thus what happens is that you could replace this C with the parameter H and U, and you want this to be equal to H, and you want to solve for, so actually call this function G, and you want to solve for this function. So what we are going to do next is going to look for just try to look for a solution and apply implicit function theorem to say there are unique solutions in a neighborhood of that solution if the derivative is invertible at the solution point. So what is this base case solution that we are going to look into are this CMC foliation in Fuchsian manifolds which come out of free. So what you have is that if you have a Fuchsian manifold, suppose in the universal cover, then this equidistant surfaces from the totally geodesic copy of H2, suppose it is at equal distance r, there is a CMCH surface with the CMC value being equal to the CMC value being equal to tan h of r. And this is what so what we want to do now is scale the given hyperbolic metric by a certain factor, so such that, we call that suppose scaling C, which we will actually define in the next slide. So suppose you started with just the H, then the Epstein surface would be this totally geodesic copy of H2, which is preserved, as this H would be the same as the induced metric here and also on the other side. But then you could scale this by certain factor, which is F, so that this corresponding CMC Epstein surface now is this equidistant surface. And utilizing this situation, what we are going to do is apply implicit function theorem. So first proposition that comes into play is that for every value of H0 in -1 to 1 and for every G0 in the Fuchsian set, there exists an epsilon and a neighborhood U of quasi-Fuchsian space of G0, such that for every G in this U neighborhood, for every G in this neighborhood, the manifold contains a closed CMC surface with mean curvature ranging in H0 minus epsilon and H0 plus epsilon. And what we are going to do is essentially what I said is that suppose you parameterize the quasi-Fuchsian manifold by the point as a hyperbolic metric times the quadratic differentials, and you again do the corresponding scaling of e power 2u h to get the actual complex structures that are appearing at the end, and then you do a further scaling of 1 minus h by 1 plus h to actually get solutions to your Fuchsian case, which are this corresponding equidistant surface from the totally geodesic copy. And if you write down the, so I forgot to mention that these formulas of first and second fundamental form could be traced back to the original paper of Epstein and also later on by Dumas, and also have been used by in the work of Quinn, who is Dumas' PhD student. And what we require is that this equation that you get by utilizing the formula for the first and second fundamental form is this G of H small h phi u, where this big H is the CMC parameter, this small h is the hyperbolic metric, this phi is the quadratic differential, and this u is the conformal factor giving you the metric actually, and you want this to be equal to 0. So essentially what we are trying is that if I had written down u h q h equal to h, then this minus h is equal to 0, and this is my actual g as I have written down in the slides. So given this situation, you have this equation solution near the Fuchsian at the Fuchsian locus, and what you do now is that you check at this h0 and capital H0 and small h0 comma 0 comma 0 when you put the Schwarzian to be 0 as in the Fuchsian locus, and this also conformal factor to be equal to 0 because you're already scaling by something before that, and you check down the linearization of g with respect to u, then it's invertible, and you can apply the implicit function theorem to get a neighborhood of the point g0 such that every manifold there contains a CMC surface with the CMC value in neighborhood of the given h0 that you started with. So h0 minus epsilon and h0 plus epsilon. So deforming this is what you get, a CMC surface near the Fuchsian locus. Now the next part is what we had already from these results of Matthew Packard and Quinn, which said that the ends of any quasi-Fuchsian manifolds are foliated by these CMC surfaces with the CMC value ranging in -1, -1 plus epsilon and 1 minus epsilon, 1. And the proof is exactly the same, where you write down the equation of an Epstein surface, and you write down the equation of the mean curvature. And what you want is that now you want to put this h is equal to -1, and you check that for any value of h050 you have a solution if you had put an h equal to -1, and this allows you to say that for any quasi-Fuchsian manifold this result holds true, as you could parameterize any pair. And again you check the invertibility at the required point, and this is invertible, and so we apply inverse function theorem again to recover the statement. So we just make one comment that this is very similar to Quinn's technique of showing that these ends are foliated by quasi-Fuchsian manifold, but the only difference we have is that this epsilon we get here is dependent on neighborhood u rather than the specific manifold that we are treating. So this is uniform over all the manifolds in this neighborhood u, and yeah, so this will be useful in constructing this open set essentially as this intersection of all these open sets that we had constructed till now around the Fuchsian locus. So what I'm saying is that now I want to show that there is a neighborhood of the Fuchsian locus which contains CMC surface for any value of h in -1 and 1. And for what we do is that if you break up this interval 1 to -1 into this line, if you just see this, and then there is the Fuchsian locus here, then what we have shown is that for every value of h0 here, there is an interval which is this h0 minus epsilon h0, h0 plus epsilon h0, let's just say dependent on h0, such that there is a neighborhood of the Fuchsian locus which contains a quasi-Fuchsian manifold with that mean curvature, with the CMC surface in that mean curvature range. And suppose this interval is what you call IH0, and then corresponding to IH0 there is thus this open neighborhood UH0. What you want to do now is that you want to repeat this procedure for the ends at infinity. So there exists an epsilon, so if you had taken this neighborhood of so 1 minus epsilon 1 and -1 comma -1 plus epsilon, then correspondingly there are these neighborhoods of the Fuchsian locus because there are neighborhood of every quasi-Fuchsian. So I mean in particular the Fuchsian locus, which is this which is this set of the ends being foliated by the CMC surface. And now what you could do is that you could take such such a open neighborhood UH0 for every value of H0 in -1 and 1, barring the ends, the 1 and -1 point, because that is already taken care of by this U plus -1, or this interval I plus -1, as I call it, the union of these two ends. And since your interval -1 and 1 is a compact interval, you check first that all these collections form an open covering of minus 1 to 1, and thus there exists a finite subcover which is called this I plus minus 1 union I80, with this H0 being C1 C2 up to Cn. And what you get out of this now is that the corresponding intersections of these open sets is well defined, and this intersection is where we have a CMC surface with all values of H ranging in minus 1 and 1. So this is the construction of the open set that contains a CMC surface for any value of H in minus 1 and 1. And now we want to construct the foliation, and two important tools required for constructing this foliation would be to say that a CMC surface with mean curvature in this IH0 has the property that the principal curvatures are in minus 1 and 1. What helps you in this is that if you have a surface with principal curvature in minus 1 and 1, then it becomes easier to study these equidistant surfaces from this given surface. And essentially what we are going to show is that in these manifolds near the Fuchsian locus, if you start with a given CMC surface and you go with the equidistant surfaces from there, is what you construct the foliation out of. And we already have that the ends are foliated, so you have the ends are foliated, you just want to show that the compact part is foliated, and you could combine these two to get a foliation of the whole manifold. So as I said, this condition of the CMC surface have principal curvature minus 1 to 1 is that the equidistant surfaces form a foliation of the whole manifold. And what you require now is basically the lemma which is going to help us construct the foliation, is that if you have S and S prime be two closed CMC surfaces in the same homotopy class with the mean curvature H and H prime, and if S has principal curvature in minus 1 to 1, then if so there should not be any fear. If H is equal to H prime, then S and S prime are disjoint, and if H is equal to if H is not equal to H prime, then S and S prime are disjoint, and if H is equal to H prime, then the surfaces are the same. So what how this help is that essentially recall that our goal is to construct this map from times minus 1 to 1 to minus 1 to 1 to m, such that at each level the image is a CMCH surface. And how we are going to do it essentially is kind of restricted to these small subintervals. I can define this map in a proper way. Suppose you call that fh0, and what you want to do is now define this f restrict. So h0 is again that c1 to cn range, and what you want to do now is that you want to define this map f restricted to this open interval fh0 as this fh0. And this second point what we have is that in the overlaps there is nothing bad happening. So we have that the image is actually a CMCH surface, and from the first point we have further that this map is injective. If H is not equal to H prime, then S and S prime are not the same. And we also get the surjectivity part from the intermediate value theorem, as you already have that the foliation exists for the ends. And so if it's taking values near 1 and minus 1 and it's a continuous map, then it would take a value in between for all. And then how you check that this f is a diffeomorphism is actually by showing that the derivative of f as you move along the normal to this CMCH surface is a non-vanishing function. And if you get all of this, then what you show that this f is a diffeomorphism uh, between S and times minus 1 to 1 to m, such that at each level I have that image is a CMC surface, and this concludes the proof. Note that in this just saying that in this work we have not really assumed that our manifold is almost Fuchsian, although it answers the question in some sense. And yeah, I mean in the foliation that we construct, this H equal to 0 would be again this unique minimal surface with values of the principal curvatures in minus 1 to 1 contained in the quasi-Fuchsian manifold close to the Fuchsian locus. So this is again something, but anyway, this so utilizing this data at infinity of a quasi-Fuchsian manifold, we constructed these Epstein surfaces which we asked to be CMC, and we show that this happens near the Fuchsian locus, and then we constructed this foliation by combining these CMC surfaces with the CNC surfaces at the end that you already had. And this concludes the first part of my talk. So thank you for your attention. See you in the second part. Thanks.